welcome back. As you know, I keep using Sci-Fi's Hi-Fi 1 Ruby board for all my exercises, and Sci-Fi Hi-Fi 1 Ruby board has FE310 core in it, and the FE310 core is RISC-V 32 core with support for IEM AC extensions. And in the previous video, I have discussed about the integer or I extension. But in this session, I'm just going to discuss about the M extensions. So in the RISC-V spec, M extension is section 7. And M extension discusses about integer multiplication and integer division. And floating point is not part of the M extension. I think it's part of F extension. I'm not sure. But even in this M extension, I'm just going to discuss only about the integer multiplication in this session. And because if you want to cover both, it will take more than 20 minutes. So I just want to keep the session less than 20 minutes. Okay. So considering the multiplication instructions of M extension, it can be captured in this one slide. And it would be really helpful if you have some background on the number representation and the signed versus unsigned representation in any computer. Even otherwise, yeah, you have to, it might be a bit hard for you to understand, but of course, yeah, you can refer to some other videos to know more. So basically, these are all the multiplication instructions part of the IM extension. So this we will soon see about how to use this. But I just want to mention three things in this slide. One is, so if you multiply two numbers, each of 32 bits, then the result can go up to 64 bits. Okay, that's the mathematical rule. So it's not very difficult to understand why. Just for example, if you take 3 digits number, okay, no, 3-bit number. So let's say 7, 7. So this is 7 and 3 bits. If you multiply, you can see 49 goes up to 5 bits here. 1, 2, 3, I have 6 bits here. Okay. So that's all. So the rule is that so the result can go up to the sum of the number of bits of the multiplier and the multiplicand. Okay, that's one thing. And the second, the signed versus unsigned numbers. Okay, so the signed and unsigned are identified by the most significant bit. So if you consider this as a 3-bit unsigned number, then this is 7. But if you consider this as a signed number, then this would be -1. Okay, and that's why, so that's second thing, so signed and unsigned. But computer does not distinguish, it's all for us to understand. Okay, computer just deals with ones and zeros. That's why if you see here in the syntax, I say that RS1 or the source is treated as it's not going to be converted into a sign, or the computer or RISC-V code is not going to do anything with that. But when we read, we can interpret in both the ways. That's why. So in a nutshell, you have mul and mulh, and mulh are unsigned. So if you see the H stands for, it is gonna take the upper 32 bits of the results. That's why you have the H higher. And then U stands for unsigned here. That means both the, if you see here, both the multiplier and the multiplicand. So both are unsigned. Whereas in this signed unsigned, the multiplicand is signed and the multiplier is unsigned. And that's it pretty much. And this is the syntax. And the third point which I want to discuss in this slide is this one, that is in the RV32I core, that means the X length is 32 bits, but we have, when you multiply two 32-bit numbers, the result can go up to 64. That means that if you store that 64 bits into a 32-bit register, then you have to either take upper 32 bits or lower 32 bits. That's what this is all about. So you have a mul. If you want to take the results, if you want to uh, get the lower 32 bits of the results, and h is just upper 32 bits of the result. So these are the two variants. Then this is for the signed and unsigned. Then you might be wondering why we have to really have an instruction. Mostly it's not something new. Every processor supports that. So first, let's just run some multiplication code in C and try to interpret the results. So I have chosen the multiplication and multiplier array values to cover all the signed combinations. So let's run and see. So this is, let me change the number format to decimal. Okay. So 2 into 3 is 6, yes, and 2 into minus 8, as you can see that it's obvious that these two results are right. And now let's get into these first three values, okay? So we have 1, which is definitely something wrong when you multiply two numbers like this. Okay, let me change this format into hex. First 3 I will keep it in hex. So now we have to see if these results are right or wrong. Okay, so first one is multiplication of this the maximum 32-bit value, which is like 0x followed by 8 f's. So if you take a calculator and you can see that, so this is the decimal value for this hex value, and when you multiply with that and the result is this big number, when it's written in 64-bit result, this is what you get, and the upper 32 bits are this and the lower 32 bits are this. So from the result it seems that it has taken the lower 32 bits, okay, and it has discarded the upper 32 bits. And let's get into the next pair, which is like 0x2000 into this. So if you see here, and these are the decimal values, when you multiply, this is the 64-bit result, and the upper 32 bits are this and the lower 32 bits are this, and you can see that it has discarded the upper 32 and it has taken the lower 32 bits. Same for the third pair as well. If you see here, it has, so the upper 32 bits are 0 and the lower 32 bits are 270-570E0, which is the same here. So it's very obvious that these multiplier are the multiplication instructions in C. When you compile, that corresponds to this what do you say, this assembly instructions. I think once it's compiled, it gets it uses this instruction, because this is where you see that it just multiplies and takes the lower 32 bits of the result. Okay. What I'm gonna do next is write some C wrapper code on top of this each multiplication assembly instruction, just to make it easy to be called from this C program. So I have created a mul.s assembly file, and I have discussed this assembly versus C, how to use these variables across and how to pass this values between C and assembly and register. All this I have discussed elaborately in my other videos, so you can watch that if you have missed, and or else you can watch the links above. So if you see here, so this is the this mul instruction would return the least significant 32 bits assuming both the inputs are signed, and mulh this would return the most significant 32 bits assuming these two inputs are signed, whereas mulh-u would return the upper 32 bits assuming both the inputs are unsigned, and mulh-esu would return the upper 32 bits of the results assuming one input as signed and other input as unsigned. That's all the processor would do. But now it's up to the user to use the right multiplication assembly instruction and get the results according to what they want. So now coming back to the code, so this is where we were before, and if you consider this, sometimes the user might consider these two as signed numbers. In that case, this would be -1 and -1. When you multiply, you should get 1, and that's the result you got before. And we get when you use this. Now, if the user, or if we consider this as an unsigned number, and like here, so it's better to get the most significant 32 bits because that's a closer approximation of the result than just getting us 1. So now we know, let's say that in this case, if you want this result, then what how this code should be rewritten is, so we should consider this as unsigned and we want the most significant. So I copy this. Basically, we are forcing the multiplication program to use this particular assembly instruction. So how we do that is, so we call the assembly functions and pause these two as an argument to those. Okay, that's it. So the first argument will go in A0 register and the second argument will go in A1 register. That's why it multiplies and the result would be in A0, and we would get the upper 32 bits of the result. Okay, let's see how this works. Just go inside and you can see the registers here. A0, A1, okay, so multiply and you see the result. You can already see the result in A0 as the upper 32. Then if we step in further, and now if you go to the results and see, so you can see that I have not executed the rest of this, just want to show that now we have got the more significant 32 bits. So now if we want to the third pair of data, like the the 20,500 and 32,600, now if we modify this line and if we force that to use this instruction to get the upper 32 bits, then you would end up in getting just 0. So it's very important for the programmer to know what kind of data he is dealing with and how to interpret the result and which instruction to use. So now for this case, you see that the data on both the halves are needed. So let's see, that's the second pair for this. So if you want to get the results, that's a 64-bit result, then what can be done is half equal to, so that would fetch the upper half, and I'm sorry about this, I don't know why it's so the highlighted text keeps highlighted for a longer time. I don't know, maybe the refreshing rate of my monitor. But so we get the upper half of the result using this must be 32 into the one into a 32-bit variable in one 32-bit variable, and the other half of the result in other variable. Let's see. Okay. Let me step in. Okay, that's the first. Okay, so it's the second. So let's see the results. So variables and result. So the upper half is 1FF. Okay, and then let me step in further. Okay, and the lower half is easy to do. Okay, so if we need both the halves like that, if we need the 64 bits, if you want a 64-bit resolution, this is how then you can. Then once you get the results, then you can OR and do whatever you want. You can also round it off to the highest 32-bit value based on the sign of the input. So since the program is expected to know the data what he's dealing with, then rounding off and all this is left to him to decide how to handle this. So I have covered pretty much the basic multiplication assembly instructions of RISC-V. So we have come to the end of the session. But if you want to learn in depth, or if you want to learn more about this multiplication, RISC-V multiplication assembly instructions, then I would recommend you to try to implement 3x3 or 4x4 matrix multiplication, because matrix multiplication would include not just multiplication, it's like a multiplication and accumulation. So thank you.